Okay, so we've been talking about conservation of momentum. It follows on directly from what we've talked about in terms of conservation of mass. The two are complementary. Remember that when we did Bernoulli's equation, we had Bernoulli's equation, which is conservation of momentum, and conservation of mass, which was the equation we used to get closure if we had two unknowns in our six variables for Bernoulli's equation. If we had two unknowns, then we had to use something else to close the equations, which was conservation of mass. Bernoulli is written kind of streamline-centric. Reynolds transport theorem for each of those conservation of mass and conservation of momentum allows us to look at kind of arbitrary shaped control volumes, and that's all. And it involves an expression that looks like this. So this is perhaps the best expression to recall. Remember that we often write it just as a summation and throw away the integrals. So it's a summation of velocities. Let me just write them down first. Well, I'm going to write this down as this, right? Mass rate of flow and equal to the sum of the forces. We know that these are vectors, so that each of these have components in x, y, and z. We'll remind ourselves that this is the velocity relative to the control surface. And so I guess should say maybe the fluid velocity relative to the control surface. And this is the velocity of the control surface. And yeah, and so this we have to use the appropriate sign convention. And so we know that if we have a volume which has fluids going into it, then we know that the sign convention, just to repeat this, I don't mean to repeat this, the sign convention here is positive for the mass flow rate. This would be negative for the mass flow rate. And this would be for both W or for the velocity of the control surface, this would be positive. Right? And this would also be positive for both W or velocity of the control surface. So those are the important things I think you need to remember. I would encourage you to look at the end part of last on Wednesday's class 7.2, I guess it was. Yeah, because I think this kind of idea of a moving control volume for momentum transfer kind of encapsulates what's going on. Since we didn't go through in class, I'll very quickly go through the last example that I tacked onto the movie, and that is the sleeping giant, the so-called sleeping giant, which was the gas cylinder. Okay, and so I don't know. You can look on online for this. So I don't mean to cut you off by doing this, but I did. So just look at linear momentum, conservation of, and this is moving control surfaces. Okay, and so the sleeping giant. Remember the sleeping giant? How are we going to do this? This is the best drawing ever. Doesn't that just look like a gas cylinder? You're going to cut the head off, decapitate. And so this is the gas cylinder. This is X. I guess this could be Z, it could be Y, it doesn't matter. We've always taken Z as upwards. We're only going to look at horizontal behavior. So moving along here. And what do we want to do? Yeah, okay. So let's define a force that we have to apply to this. in the x direction to keep it in place. Let's define the fact that we've cut the head off this, and there's a velocity coming out, and I guess we can just call that whatever this is. Let's call it 1 meter a second is the velocity, and let's have the mass rate at that velocity be 1 kilogram per second, right? So there's something coming out of here. The only place it's coming out of is at the tail end of this decapitated cylinder. This would be the nominal scalar magnitude of velocity. This would be the nominal scalar value of mass flow rate. No directions. I'm writing them specifically as that. So it's coming out the backwards. It's pointing towards the minus x direction, and it's 1 meter a second, and it comprises 1 kilogram a second. So if you take our expression, which is just the sum of the velocity relative to the control volume plus the velocity of the control surface times the mass flow rate is equal to the sum of forces. We only have one set of forces here, so I guess we could write this as this. And it's in the x direction only, right? So that's our basic expression for this. We only have one outlet, so we only have one velocity here. I guess we have a velocity of the control surface of this thing moving. And so we have a couple of options. So we can substitute some magnitudes into that. And the important thing is we can do it in two ways. We can, first of all, we know that the velocity coming out of here is what magnitude? And so the velocity here is velocity in the w direction. It's going to be equal to the coordinate system. It's in the negative x direction. So this is going to be minus 1 meter per second. The mass flow rate is going to be 1 kilogram a second. It's in the out direction. It's flowing out of here, so it doesn't matter what the global coordinate system is. So this is a positive. And there's a force applied. So basically this is going to be, if you want to substitute these values, 1 meter per second plus the velocity of the control surface times 1 kilogram per second is equal to whatever the force is applied. And so there are two modalities you can do this. Actually, there's an infinite number of modalities, but the two n-member modalities are, one, you can apply force so it doesn't move, in which case the control volume has to be 0, velocity control volume is 0, and there's a force applied. Well, the converse is you release the force, it moves, and it goes at some steady velocity, but the force that you apply is 0. So those two modalities, if you like, that you can apply to this would be if you hold it, and so, no, yeah, okay. If you hold it, then the velocity of the control surface is equal to 0. If the velocity of the control surface is equal to 0, then the force in the x direction, by definition, has to be the product of 1 times 1, so 1 kilogram meter per second squared. Kilogram meter per second squared is a Newton, right? So this is equal to 1 Newton. And there's a minus here, and so this goes here. And so it's saying that the force that you have to apply here is a force pushing in this direction, the minus x direction, to hold it in place. Absolutely reasonable, right? It's pushing against you, you're holding it here, and so you have to push in the minus x direction to do it. And this is the force you'd have to apply. If you take the converse and you release it, release Roger, then the force you're going to prescribe is 0. If the force is 0, and then this is the unknown, the only way that the force can equal 0 independent of this mass flow rate is if these two numbers inside the bracket balance, and so the velocity of the control surface in that case has to equal plus 1. And perfectly reasonable as well, bless you. And so you hold it, it's static, and you apply force, you calculate the forces, you push the force in this direction, right? If I'm looking at it here. To be able to, I'm pushing against this because it's trying to travel towards me. If I release the force, then it's happy to slide, and it will slide towards your right, and my right, I guess, on this as well. That's it. And so that's kind of curious because what we'll talk about today is linear rotational momentum, which is more useful for some machines. But for instance, if you thought of this as a machine that you wanted to get work out of, then it's interesting to plot up on two axes the magnitude of the force that you have to apply to it in the x direction. Ignore the fact that it's negative or positive. And the velocity which the control surface might move at. Okay? So if the velocity of the control surface is 0, then the force that you apply is 1 Newton. If the velocity of the control surface is equal to 1 meter per second, then the force that you apply is 0. So the two ordinates on this graph are exactly this. Our reason for looking at this graph is that the work that's done, which is the rate of doing work, which is power, is going to be the product of a velocity. Could be a velocity times a force, right? Force times length is equal to work. Force times length per time is rate of doing work, which is power. So force times length, force times the distance traveled is the work done. Force times the distance traveled in a given time is the rate of doing work, which is the same as power, which is in watts. And so the interesting thing here is at this point, there's no work done at all because you have a force that's applied, but it's not moving. Here you have no force, but you do have a velocity, and so in each case the work is equal to 0. But if you look at providing some kind of linkage to this, so you're pulling against it, then somewhere in the middle of here you actually are doing some work, right? So maybe a half Fx and maybe a half velocity of the control surface, you're doing some work. And so in other words, at this point, the amount of work you would be doing would be equal to a half Fx times a half VCS. And this would be the magnitude of work. So I guess if you plotted, for instance, the amount of work done as a function of how quickly you're going in this particular system, it would look something like this. I don't know if it would certainly be 0 here, and it would be 0 here because of these 2 points, but it would be some different magnitude here. So I think that's an interesting way of looking at it. It's probably not so, I guess we're probably not going to harness a bunch of decapitated cylinders as machines to generate work, but if you look at the example in the text of a vane, you know, this thing you're squirting a fire hose at and it moves down the road, it's really no difference from a Pelton wheel going around, but it's just being pushed. And so this is kind of the preamble to be able to talk about work done in linear momentum. And so the other interesting thing, so everyone's fine with that? So the other interesting connection with that, I think anyway, is to look at, say, wave power. And so you certainly have all the facilities to be able to figure out exactly what would happen if you'd have a buoy or a buoy that was in the water. And say the wave heights do this. Where this is delta H. So this is from peak to crest of the waves that wrap over this. So this is a buoy that sits in the ocean. If it goes up and down with the waves, well, that's great. If there's no force attached to it, it'd just go up and down, it would move. And so I guess it would be like this point, there'd be no force attached to it, but it would move, so no power. If you anchor it to the seabed, which I guess you'd want to do, if you anchor it rigidly so it can't move, then the water will wash up and above it and down it. And of course, as the water is at this level versus this level, this change in elevation would change the buoyant force because the water level is coming up, right? You have more displaced water as the water rises, so there's a buoyant force. But if it's rigidly anchored to the seabed, it's not moving, and so there's a force, but there's no velocity or no displacement. And so those two end members, you're at these 2 points. So I guess what you need is to be able to attach it to the floor so there's some actual give in this. This isn't a resistor. It's a mechanical resistor. It could be an armature, I guess, of a electric motor for that matter. And you'd be able to get be able to use this in some useful way. So in other words, the buoyant force that you'd have acting as this goes up, you don't have to worry about anything else. If you can remember, is unit weight of water times the volume displaced, which is going to be unit weight of water times the cross-sectional area times delta H. And the velocity of the control surface, I guess, is going to be what? If you allow it to go up and down with the motion of the ocean, it's going to go up, say, a meter in a regular wave. I don't know what it would be. And so it would be 1 meter. And I don't know what is it between waves? Is it 10 seconds between waves? As they wash in on the coast? I have no idea. So if that means it would go up a meter it would go up and down a meter every 10 seconds. So I guess that'd be 2 meters every 10 seconds. Let's make it 2 meters every 20 seconds. So that's a meter every 10 seconds. So a meter every 10 seconds is 0.1 of a meter every second. So 1 meter in 10 seconds equals 0.1 meters per second. And again, you can combine those in this little idea of a diagram of the velocity of the control surface, the force, in which case this is a buoyant force, and doesn't do anything if it's rigidly attached to the seabed. We have a force but no velocity. If it's just floating on the sea surface, we have a velocity but no force. And so maybe we want something in the middle here. So maybe we want the actual work that's done out of this being equal to a half the buoyant force multiplied by a half the velocity of the control surface. And if we throw, bless you, if we throw some numbers in that, bless you. Buoyant force, so what is this? 1 meter squared. 1 meter height, so what is this? This is, unit weight is 10 kilonewtons per meter cubed. Area is 1 meter squared. Height is 1 meter. And velocity is 0.1 meters per second. So the 10 and the 1 drop out, so we end up with actually quarter of a kilowatt. Yeah, so interesting. So I think the idea is interesting that if you hold it rigidly, you have a force, but you're really not doing any work because it's not moving. You allow it to go on its own. It'll take up the velocity of the free surface of the ocean, but still you won't get any work out. But to get any useful work out of it, you have to act against it in some way. And so I think that's one curious outcome for this. All right, so relatively straightforward. So very simple example, but yeah, kind of a cool calculation. So a quarter of a kilowatt is 250 watts. So that's 2.5 incandescent light bulbs, I guess, right, of that order. Okay. All right. So there's method in the madness, of course, and so that was kind of to introduce this. So remember the sign conventions for this. Remember this kind of interesting issue here that the mass flow rate doesn't matter. The velocity of this cylinder, if we release it, is the velocity of the gas coming out of it. That's the equilibrium velocity if there are no forces acting against it. Of course, there would be friction on the floor. There would be, if it was airborne, for instance, there would also be drag, air drag around it, but we're not worrying about that. And so it works out to be a very simple component. So if you're thinking about a form of this equation to remember, then this isn't a bad form. This is the most complicated form that we'll use it in. And of course, if it's a static control volume, then this just gets thrown away. So it's easy to think about that. All right? So, that is an entree into us talking about work and machines. All right, so let's see what we've got. So we've obviously got some silly things that we could look at, that we will look at in this, this session. The most simple of things is a garden sprinkler. In this case, the dog running around it for laughs. But again, the same applies. So we could calculate what the work would be done by this if it's free spinning. No work, right? Because we're not harnessing it. We're not applying a force against it. If we clamp it and hold it, we have to act against it, but then it's not rotating, and there's no work done there either. And so to get work out of it, it has to be at this intermediate state where it's spinning, but where there's a load applied to it. And of course, that isn't really much different. It's a very simple machine to think about, but it's not so different from, I don't know what's coming up here. Oh yeah, this is don't do it at home without protective clothing. But the basic idea here, I'm hoping that all these have the sound turned off, otherwise you won't be able to hear me over. So this is taking a bottle, filling the bottle with liquid nitrogen, and then putting a couple of straws in the bottle so they're slightly displaced, so that when you put the liquid nitrogen in the bottle in some warmer water and it evaporates and comes out the straws, it's a little machine that rotates. And so it's the same principle as the garden sprinkler. I'm not sure I wouldn't be doing this without gloves. Of course, you can burn yourself just as easily with cold things as you can. And so he's going to put this little sample. They're just two straws sticking out that he's twisted so that they're not pointing straight up. They're kind of angled. And then as you evaporate the liquid nitrogen, you should make it by putting it into this beaker full of warmer water, or water anyway, right? It'd be warm enough, even if it's 4 degrees centigrade, it'd be warm enough. And you get a little spinning machine over the back. So that's what they do in Australia. You can see from the website, com.au. Okay, and then real world stuff. I'm not sure exactly what we see here, but if you think about hydroelectric power, the mechanisms by which electricity is generated as it runs through a dam is by using turbines, and turbines are just a more complicated way of doing this. You allow a flow to occur through it. I think this is ramping up. But you've seen this one for sure. We looked at this last time. This is the simplest way. This is kind of a Pelton wheel, which is really just the old water wheel, overshoot, undershoot water wheel idea. That is to squirt air onto these little cups. They move it just like the vane in the last question that we did last time, which is on video. But instead of the vane moving horizontally, linearly, it's actually attached to a contour that forces it to go around the circle. And so it takes linear motion, which is water or air moving linearly, and turns it into rotational motion, which of course is useful to attach to an armature to be able to generate electricity. And I thought this was kind of cool as well. Das Leitrad befindet sich die Spirale oder auch Schnecke genannt, die das Wasser zusätzlich in Drall versetzt. Das Wasser gelangt über ein Zuflussrohr in die Spirale, das vom Oberbecken des Pumpspeicherkraftwerks kommt. Das Abflussrohr leitet das Wasser ins Unterbecken. Das Wasser durchströmt das Laufrad und versetzt es in Rotation. Dadurch dreht sich auch der Rotor des Generators und erzeugt somit Strom. A catcher on it, which dips into it. It puts water in it, and it's almost like an Archimedes screw, right? And it allows that water to be pushed down this connection in the center of the rotation axis. So, kind of a clever idea. Here you're making the stream do work for you to be able to put water out of the stream into an irrigation field or into someone's house. So, kind of a simple idea, but quite clever, I think, right? It is an Archimedes principle Archimedes screw in a different way. Not Archimedes principle in terms of buoyancy, but Archimedes screw. Okay? And I guess I don't know whether we have something useful on this, or it's already finished. It's in German as well, so
Francis Turbinen.
It won't help you. So this is the idea. You have a dam with a reservoir, upstream reservoir, downstream reservoir. You run it through turbine at mid-height. You take kinetic energy, you take potential energy, turn it into kinetic energy, and then turn that kinetic energy, which is linear, into rotational motion, which is then turned into electricity. And so you squirt water either into here and then out through the side, or in, I guess in this case, yeah, in through here, and then it turns 90 degrees and gets squirted out through here, and in that it turns a blade around just like an impeller and makes linear motion, which is into this feature, into rotational motion by the fact that it has to go through here and exit out through this, and by exiting out through this it gives rotational motion. So nothing more than that. Perhaps we don't need to dwell on that. Okay? So let's talk about what we need to understand to be able to do that. And it's really pretty straightforward. You'll recall that when we talked about conservation of momentum, what we should have said that what we were dealing with was conservation of linear momentum. And now we need to talk about moment of momentum, so rotational momentum. And it's really quite straightforward. I'm not going to go back to Reynolds' transport theorem, but I will make the case that if this is our fundamental expression that we have for linear momentum, what we did was we substituted in a value for this intensive property and the extensive property, which was equal to just the mass multiplied by these two values. And so hopefully you can see some kind of symmetry between this term here and say this, the control surface isn't moving, and this term here, which is this. And so all we're doing is that we're taking a velocity here and we're kind of multiplying it by a lever arm, and then the force that actually ends up here is also a force multiplied by a lever arm. Force multiplied by a lever arm is a moment, and a moment, if it's moving or stopping motion, is a torque. And so that's the connection that we're attempting to make. So we'll use an expression like this to be able to solve some problems. And this expression will actually boil down to something a bit more simple. And the bit more simple expression is this, is that the torque we get on the shaft is equal to the moment arm, the velocity that squirts out of our sprinkler, and the mass flow rate of that. And so that's where we want to get to. Okay? So take that on trust for now. A little bit of what we need to know first. When we dealt with mass flow rates, we talked about dot products and what those mean. It means that we get the component of velocity perpendicular to the surface that it's coming off. If we look at the ideas of moments of momentum, the idea is pretty straightforward also, and that is if you have a pivot point, and if you have a force which is acting at a location with some lever arm, this is R is the lever arm, then to make it unique, we need to be able to not take this lever arm in an arbitrarily oriented force. We need to take the lever arm where the force is at 90 degrees to that. And so instead of, although the force acts through this point and with this lever arm, to be able to uniquely define the moment, we need to have it act through this length here. So the moment in this particular case is going to be equal to, so this is moment, not mass rate. So let me write that out. It's going to be equal to what? It's going to be equal to the lever arm multiplied by the force. The force, of course, is a vector, and this is its magnitude, but it also just has a length. And in this case, this value of L is going to be equal to what? The length is equal to the location to where it acts multiplied by the sine of theta. This length here is just equal to R sine theta. And so if you put this into here, you end up with the moment being equal to, just making the substitution, F times R sine theta. So this length here is just what we've called lowercase l, and this is the magnitude of the force, not as a vector, just the magnitude. And so this moment allows us to be able to calculate this behavior just by looking at this. And of course this, actually, what we've done here is the cross product. It's the cross product of the vector r and the vector f, which we just write this way. And so we really only need to know it in this form, but it's perhaps useful to think back to what your vector calculus was. The basic idea is that we can take this value. If you want to think about cross products, I'm not sure whether we do or not. I mean, you can just do this arbitrarily for your coordinate system. Yeah, perhaps I'm doing you a disservice if I don't talk about it. Right-hand coordinate system, x direction, y direction, z direction, which is what you have here. If you have the correct orientation, I guess in this case, I'm not sure I can do it. Right, this is it, right? Yeah, it is this one. And so that's exactly what you have, x, y, and z. And I guess in this particular case, in the y direction, you have a vector that's this, right? That's what is up on the board. So there's a velocity that's moving at the tip of my y finger, and that is, if you want to calculate what the moment arm due to that is, you can just use the cross product. And it's relatively kind of straightforward math. And that is that in this particular case, this is the location where it acts. It has some velocity. So this velocity vector would be -1 in the x direction because it's going in the minus x direction. And it's perpendicular to both y and z. And so each of these are 0, right? So this is the velocity. This is the vector that has some magnitude 1 that's going in the direction of this arrow, just by definition. The location where it acts is at this point, which is 0x, 1y, so this is, I guess this is 1y, and 0 in the z direction. So I, j, and k, it has a magnitude 1, which is the point where it acts here. So those are the two pieces of information we know, because rather than look at a lever arm and a force, we're going to look at a lever arm and a velocity in these, right? So this is this. And so the lever arm times the velocity is just the cross product. And the cross product are the coordinates of this coordinate system. I is in the x direction, j is in the y direction, and k is in the z direction. These are the magnitudes of the location where the point acts. And so in our particular case, this would be equal to 1, which is this term here. And in our particular case, we have a velocity in the x direction, but nothing in the y or z. And so this magnitude here is equal to -1. And that's it. And these values are 0. This is 0, this is 0, this is 0, this is 0. And so the cross product, if you remember how you multiply these things out, do you remember how to multiply them out? You multiply this by the product of these two minus the product of these two. This times the product of these two minus the product of these two, which is this. And then you subtract from that this multiplied by the product of this minus this and this, just symmetric. And then you multiply this by the product of these two and these two. It's just the determinant of this component. So go back to your vector calculus and remember that. So the only thing to remember is that this line here is the same as this. This line here is the same as this. And if you do those multiplications, the only actual terms that you get out of it, this is a 0, this is a 0, and the only term you get out of it is 1 times -1 times +1, which is equal to, is that a yawn? Which is equal to 1 times k. And it's what you know, right? The lever arm is 1, the velocity is 1, so the product of those two is 1 times 1, and it happens to be positive, again, because of a sign convention. And the sign convention is that we've used x, y, and z, but the sign convention for these rotational velocities is the right-hand convention, which is rotation in your direction of your fingers, and this is the axis. And so in this particular case, we have the vertical axis, which is z, which is my thumb, and the rotation that we have due to this velocity is in the direction of my fingers. If you look, I guess, if you look down on this, it's counterclockwise. I suppose if you look along the axis, it's clockwise. And so this is the positive rotation, and therefore this magnitude here is plus 1. Okay. So that's cross products and how it relates to what we're doing. You don't need to know that, having said that. You just need to be able to use this in a slightly abridged version. And so I'm not going to go through this, but you remember that before we used Reynolds transport theorem, we had mass times velocity, and we had this extensive property and the intensive property, which is just this divided by mass. But now we have a velocity multiplied by a lever arm. If we substitute that into Reynolds transport theorem and play around with some things, then what comes out of it is that we end up with, instead of just a velocity here, we have a velocity with a lever arm, which comes from this term here. We don't care about the time-dependent part, too difficult for us. And in this part, we have a force multiplied by a lever arm. And so this force multiplied by a lever arm, which comes from this, right? This is velocity times density times volume. So velocity times density, so density times volume is a mass. Velocity times mass is momentum. Rate of change of momentum is force. So this is Newton's law multiplied by a lever arm. Newton's law multiplied by a lever arm. So it's not important that you know where that comes from, but that is where it comes from. And so how do we use it? So let's go about a quick example to be able to show how to use it. We have the basic expression that we're going to use, and that expression is going to look like this. Okay? So the other thing that we need to also recall is that what we've called is that V static is equal to the velocity relative to control volume plus velocity of the control surface. That's how we've called it in the past. And this applies here as well. It's kind of important because we have these two conditions. You either clamp the thing and you squirt and you apply a force, a torque in this particular case, or you let it free, allow it to rotate, and you don't have a force, but you have a velocity. And so the essence of what we'd like to do is be able to incorporate this velocity into what we're dealing with. Okay, so don't worry about the derivations, but remember this expression here. This is basically R times F. Shaft force is equal to the lever arm, the velocity, the water comes out, tangential to the control surface, and the mass flow rate. So let me draw that. So you're looking down on this sprinkler. Velocity comes out at some angle. This is V theta. This is the radius. This is the radius here. This is the velocity, which is tangential to this control surface. And so, for instance, if you had a velocity coming out here at some angle theta, then the component here, so if this was V out, so V theta would be equal to what? It would be equal to V out, but the component in this direction, which is V out cosine theta. And so always we relate these velocities not now to some arbitrary, well, it's the same as these velocities are relative to the x, y, or z directions when we look at linear momentum. Now they have to be relative to this coordinate direction, which is the only unique coordinate direction is a tangent, if you like, to the rotation surface. And so this is this, and this is the mass flow rate out. So out is positive. I don't know if it matters actually, because yeah, it doesn't matter. Out is positive for the mass flow rate. And so the idea is that if we can calculate what the shaft torque is, for instance, if we know what the velocity is and the mass flow rate and the radius, we can calculate this. If we know what the shaft flow rate is, we can multiply that by the rotational speed in radians per second, omega, and that will give us the shaft power. This is power. In other words, watts. W is for watts. And so you can work out what the power would be from a turbine. So, okay? Everyone okay? So you'll only ever have to use this one expression that we have outlined there. So it's a straightforward one to work with. All right, so a quick example. It's in the book. You can have a look at it at your leisure afterwards, but let's go through it. Basic idea is you have a spinning wheel. It actually has this trident form with these three outlets. You have water that spits out of here at some velocity, and this nozzle is angled at an angle theta relative to the tangent velocity. So this is the velocity it comes out at, and so v theta, if you like, is equal to just this velocity times the cosine of this angle for the reason we just said. We know how much is coming out. It's coming out at a mass flow rate, a volume flow rate of 5 liters a second. We know the areas of the nozzles which it comes out at. So we know the area of each one of these nozzles. We know the volume flow rate, which is equal to 5 liters a second, which is 5 times 10 to the minus 3 meters cubed per second. We should be able to calculate the area. And so how do we calculate these two conditions? End member 1. Clamp the unit so it can't twist, and then calculate what the torque is that you have to apply to keep it there. This is the expression here. Mass flow rate, the radius, the velocity, v theta. And so we know the velocity coming out here because we know the volume flow rate and we know the cross-sectional rate. So what's the velocity? The velocity has to equal the volumetric flow rate divided by the area of each nozzle, but there are 3 nozzles, so these are the individual. So 3 times the area is the amount per nozzle. Okay? So the velocity out of the system is going to be this. We know the angles, so we can correct for the angle it's at. We know the radius, which is half a meter. And we know the mass flow rate because we know this, and we just multiply by the density to get the mass flow rate. And so if you substitute the appropriate values for the mass flow rate and the escape velocity into this expression together with the radius, you get an equation which gives you the amount of force that you have to apply as a function of a constant flow rate, a constant radius, constant density, constant nozzle exit area, and the only thing that varies is this angle. And so the calculations on the other side look at this behavior. If you look at this angle being 0 degrees, the force that you have to apply to keep the thing from moving is 230 newtons. If you angle it to 30 degrees, I think, then the force you have to apply goes down to 200 newtons. If you angle it to 60 degrees, it goes down to 116 newtons. What's the torque if you apply 90 degrees? 0. Yeah, 0, right? So if it's 90 degrees, then it's just pointing directly out here. And of course, if you put in cosine 90 as 0, you get 0 torque, which is just vindication that you're possibly right. And so it gives the maximum behavior when it's oriented tangential, and it becomes progressively smaller as you get skewed further and further out until you're 90 degrees. The opposite, I realize we're right up at the end of time. The opposite is if you now allow it to rotate. And the expression now is that the velocity that we're going to look at, v theta, is now modified somewhat. It's going to be equal to the rate at which it comes out of the nozzle relative to the nozzle, but also it's going to be modulated by the velocity of the control volume. And so this is the velocity that it's coming out of the nozzle relative to this direction, v theta. So this, if you like, is v theta. But the control surface can move because now we've taken away the lock on the torque. And so it's a bit like the decapitated gas cylinder in that we now have this equals 0. And the only way that this can equal 0 if both of these terms are non-zero. And so the only way it can equal 0 is if this term and this term are equal and opposite to each other. And so it's not so different from the gas cylinder calculation in that the velocity of the sprinkler head that it moves at has to be exactly the same as the component of water squirting tangential to the circle of rotation. For the case of the decapitated cylinder, the velocity it moves at is the same velocity as the stuff squirting out the back. The velocity of the vane, in the case we didn't do, has to be the velocity of the water that squirted at it. And in this case, the rotational velocity, or actually this is a velocity on the circumference, has to be equal to the component of the velocity which is squirted basically in this direction. So have a look at that. So that's it. So we've talked about momentum, we've talked about linear momentum, we've talked about rotational momentum. They're analogous in many ways. I think the interesting thing about them, if there is something interesting about them, is this idea of work that you get out of it. For the sprinkler, both of these two end-member cases, we get no work. You hold it static, it's not moving, no power. You allow it to rotate freely, no power either. Somewhere in between, if you hook an armature up to it, you're able to get work out of it, and you can calculate what that middle point value should be as well.